Hello, my fellow algebra enthusiasts. We are here today to talk about some polynomial functions. This video is going to go with your 5.1 polynomial definition sheet. You'll see that I have it all filled out for you already, but this video is going to kind of show you the characteristics that I am mentioning in that document and give you a sense of where those graphs come from and how some of the vocabulary works. Okay, so you'll see that there's 4 functions given to you. The very first one is x squared, then x cubed, x to the 4th, and x to the 5th. So starting with x squared. Okay, so the parent function of any graph is just like the most basic bare bones function possible. So for instance, a quadratic. You guys saw in your last unit that quadratics come in 3 main forms. There's standard form, which is ax squared plus bx plus c. There's vertex form, and there's also factored form. And all of those obviously produce parabolas, aka quadratic graphs. And that's true. But in its most basic bare bones form, the parent function of a quadratic is this guy right here, x squared. If you just have x squared, then your a value is 1. Obviously, it's still quadratic because it is x squared, but you have no middle term and you have no c term. And that is still technically a quadratic. We call that the parent function, and it's the most basic one. Notice it is centered at the origin. The vertex is at the origin. The y-intercept is at the origin. The x-intercept is at the origin. It's as most boring basic of a quadratic as you can get. Okay. Well, certainly, as you guys saw, not all quadratics are centered at the origin. So I'm going to use factored form here to produce a parabola that has 2 x-intercepts, one at -1 and another one at +3. And so certainly not all parabolas are centered at the origin, and not all parabolas have x-intercepts either. So you saw that parabolas sometimes are way up here if we shift them up. And so now this parabola doesn't even have any x-intercepts. So that can certainly happen. And you also saw that quadratics are not always concave up. Sometimes they are upside down. And so certainly that is something else that a quadratic is capable of doing, is being reflected upside down. So in general, the main takeaway message here is that while yes, the parent function is just a boring parabola centered at the origin, not all parabolas are centered at the origin. We can shift them, we can move them, they can have 2 x-intercepts, and they can also be upside down. So what I'm now going to move on to do is talk about those same things, but with higher power functions. So let's start with what we call cubic, x cubed. So this is the parent function of x cubed. So first and foremost, you'll notice that it's not a parabola anymore. It does not have that U-shaped graph that a parabola has. And so one of the reasons, or probably the reason actually, not one of, but like the reason why this graph looks the way that it does in terms of the negative direction and then also the positive direction is because we are talking about a cubic now. So if I plug in, let's say -2, well, in a parabola, it would just be -2 squared. So the answer is positive, which is a good way to understand why a parabola's arms in its most basic form open upward. But now we're talking cubic. So there's a third -2 that's going to get multiplied. And so now you have a negative times a negative times another negative, and that all of a sudden produces negative answers. So absolutely, when you're talking about a 3rd degree polynomial, you do have some answers that are going to come out negative. Now, certainly if you plug in a positive though, well, the answer is going to be positive. So check it out, plug in just regular 2, and now the answer is a +8. So because of what it means to raise something to the 3rd power versus what it means to raise something to the 2nd power, you're definitely going to have a different shaped graph when you have a 3rd power versus a 2nd power. So this graph has a negative arrow down here going on forever and also a positive arrow up here going on forever. Notice it's still centered at the origin. The x-intercept is at the origin. The y-intercept is at the origin. Boring, boring, boring. That's because it's the parent function. But what is a third power or third degree graph capable of? So I'm going to use factored form. So this has an x-intercept now at -2, an x-intercept at 3, and an x-intercept at, how about 5? Let me fix my window so you can see what's going on. Okay, so first and foremost, how do I know that this is still a third power graph? Well, if you come over here to my factored form, if I were to distribute this, and no, I'm not going to, but if I were to, I would have x times x, that makes x squared, but then times another x, and that would definitely make x cubed. So this is still a third power or a third degree graph. And you'll notice that the end behavior is still the same, where the arm on the left goes down forever and the arm on the right goes up forever. But it's that middle behavior that's gotten a lot more interesting. So I've given it 3 very distinct x-intercepts, thanks to my factored form. I can also see that it's got a high point and a low point. And also the concavity of it, it has 2 very distinct concavities. Like right here, it is very much concave down on this entire side, that's concave down, but then eventually it switches to concave up. Now a parabola could never do that. Parabola is either concave up or down, but now this third degree or cubic graph has 2 concavities. And it also potentially has 3 directions. So check it out. The parent function is just one directional. It's up the whole time. Watch, I'm going to drive my car. Up, 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 and still up, 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 up. So the parent function only has one direction. It is increasing the whole time. But will they all be like that? No. So a cubic can have up to 3 directions. Check it out. I'm going to drive my car now on the green curve. Uphill, that's one direction. Downhill, that's my second direction. But then back uphill, that's 3 directions. So a third degree polynomial or a third power function can have 3 directions. Do they all have 3 directions? No. Can it have 3 directions? Yes. And then like any parabola, like you saw in your transformation activity, it can also be reflected. So as soon as I put that negative out there, that negative a value, the negative multiplier, now my end behavior, my arrows are the opposite. So notice now the arm on the left goes up, 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 up. And now it's the arm on the right that goes down, 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 down. And does this graph have to have 3 very distinct x-intercepts? No, I could shift it down. Now it only has 1 x-intercept, but it's still a third degree graph. It still has 3 directions. I just changed kind of where it's sitting on the graph paper to give it not 3 distinct x-intercepts anymore. So that's what I was trying to capture on your papers. You'll see that the parent function is just an increasing graph, but what it's capable of are those other 2 pictures that I've provided there. Okay, let's move on to x to the 4th. All right, so the parent function of x to the 4th looks a lot like a parabola. But be careful, we actually don't call it a parabola. Parabola is the word for a quadratic graph and a quadratic graph only. So it's not a parabola, but it is kind of U-shaped still. It has arms that both point up on either side. And if you think about why that's the case, it's because we are talking about a 4th power now. So if I plug in, let's say a -2, my answer is going to be a positive. Negative times a negative times a negative times a negative is going to be a positive. When it was cubic, I got a negative answer. That's why the arm went down on the 3rd degree polynomial. But now that I'm talking a 4th power, I get a positive. And certainly if I plug in a positive, I also get a positive answer on that side too. So for a 4th degree graph, you plug in negatives, you get positives. You plug in positives, you get positives. That's why the arms are both up. Okay, that's a parent function. But what is it capable of? All right, I'm going to use factored form again. So this guy is going to have an x-intercept at -5, at -1, at +2, and also at +4. Okay. Actually, let's bump that out further so that you can see that it's not always symmetric. Okay, there we go. So again, I gave it factored form so that I knew where my x-intercepts were going to be. And I'm not going to distribute this, but can you imagine you'd have x times x times x times x. That would definitely make a 4th power. Now let me change my window so you can see. I need a really big window for this one. There we go. Okay, there you go. Check it out. So this is an example of what a 4th power graph is capable of. Now notice in its end behavior, it still has arms that go up, just like the parent function, because eventually everything that we said a minute ago is still going to end up ringing true. If I plug in a negative, 7, I'm going to get a positive answer out of that, because eventually -7 times -7 times -7 times -7 will produce a positive answer. So eventually you still get the same end behavior, but it's what happens in the middle that can turn out to be very cool. So this particular graph, I purposefully gave it 4 very distinct x-intercepts. Do they all have 4 x-intercepts? No, they do not. Like, I can shift this puppy down. Oh, gotta go more. There you go. How about that? So now it only has 2 x-intercepts. So do they all have 4 x-intercepts? No. But can they have 4 x-intercepts? Yes. Notice the end behavior is still the same, but now it's got some peaks and valleys and high points and low points. So what a quadratic is capable of is definitely very different than the parent function. Now notice this is a 4th power graph, and watch this when I count my directions. I'm going to drive my car. Ready? Down. That's one direction. Up. That's direction number 2. Down. That's direction number 3. And up. That's direction number 4. A 4th power graph can have up to 4 directions. Do they all have 4 directions? Nope. Because check it out. The parent function only goes down, then up. That's only 2 directions. But it can have up to 4 directions. And also look at the concavity. The original graph, concave up. That's it. But what it's capable of, you've got concave up, then concave down, and then concave up again. So potentially it has 3 concavities, up, then down, then up. That's 3. So this gives you a sense of what a 4th power graph is capable of. And once again, notice the end behavior is still arms up because of that 4th power. It's going to turn all your negatives into positives eventually. So it still has arms up, but the middle can certainly turn cool. And just like before, if I wanted to, upside down. So check it out. Now it has no x-intercepts at all, but it still has 4 directions, up, down, 1, 2, 3, 4. It still has some peaks and valleys, maxes and mins, and it still has 3 concavities. Concave down over here, then concave up, and then concave down. And notice, just like the parent function has arms both up, well, now that it's reflected, it's arms both down. So anytime you have an even power, you're either going to have all positive arms, arms up, or all negative arms, arms down. You're not going to have one of each if it's an even function. Whereas now check this out, x to the 5th. Okay, so this graph looks an awful lot like x to the cubed, x to the 3rd power. So, well, think about why that's the case. Why aren't both of my arms up right now? What would happen if you plugged in -2? and you had to times it by itself 5 times in a row, you're going to get a negative answer. We're talking powers of 5. -2 raised to the 5th power. You're going to get negatives out of that. And then certainly on the positive side, if you plug in +2, well, then you would get a positive answer. But since we're talking x to the 5th right now, if you plug in a negative, you absolutely get a negative answer. And if you plug in a positive, you get a positive answer. You do not have arrows in the same direction if it's a 5th power or a 3rd power graph. You have one arm down and one arm up. What I'm referring to right now is something that we eventually call the end behavior. You'll see that on the note sheet, end behavior. So that's the parent function. Notice though, in terms of directions, this graph is increasing and increasing only. If you're driving your car, you're going up, 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 up. The drive got boring for a little while, but then up, up, up. It's just upward the whole time. But is that what all 5th power graphs look like? Oh my goodness, no. Check it out. Let's use factored form. So let's give it an x-intercept at -5, an x-intercept at -3, an x-intercept at -1, another x-intercept at 4, and another x-intercept at 6. So I got 5 of them there. Let's make sure. If I were to distribute this, I would have x times x, that's 2, there's 3, 4, and 5. Okay, so if I were to distribute this, it is absolutely a 5th power graph. So let me change my window so you can see all the fun aspects. Okay. Nope, still not high enough. Just kidding. Let's go -700 all the way up to 700. Barely. Okay, so check it out. Look at this. Look at what it's capable of. So one thing to notice is that it still has the same end behavior. Check out this blue graph, even though it's doing all sorts of cool roller coaster things in the middle. On the left-hand side though, eventually, arm down, just like the parent function. And on the right-hand side, eventually, arm up. So this graph would still have arrows, one down and the other up. Now all the middleness, well, yeah, that's where it gets fun. So I gave this particular one 5 very distinct x-intercepts. And that's because, yes, a 5th degree graph can have 5 x-intercepts. Do they all have 5 x-intercepts? No. Can they? Yes. Let's count the directions. If I drive my car, I'm going up, that's 1, down, 2, up, 3, down, 4, up, 5. 5 directions on a 5th degree graph. And in terms of concavities, what do I got? So it starts concave down. This little area is down, but then it switches to up. Right now I'm in the up section. Then it switches to down, concave down right here. And then it switches back to up over there. So let's see, down 1, up 2, down 3, up 4. There's 4 concavities on this graph. Do all 5th degree graphs have 4 concavities? No. Look at the parent function. Concave down on the left, concave up on the right. 2 concavities, that's all. Boring. But what is it capable of? 5 directions and 4 concavities. And then, as you've seen before, that entire image can get reflected. So now, instead of the left side being negative, well, now the left side is the positive arm, the upward arm. And instead of the right side being positive, like the parent function would say, now it's reflected and it's the right side that goes down, down, down into the negatives. But nonetheless, they still have arms in the opposite direction because it is indeed a 5th degree graph. So the same way that a 5th degree graph produces negatives and positives, aka one arm down, the other arm up. Well, even when things get weird, it still has one arm up and the other one down. So that's something that happens on your odd functions, because eventually if you plug in a negative, you'll get a negative answer. If you plug in a positive, you'll get a positive answer. But we can also reflect that. So opposite arms, whether it's reflected or not, opposite arrows. Okay, and that gives you a sense of where I was getting my pictures from when I drew them for you. I know the one that I drew for your 5th degree graph is shifted way down too, because it has no x-intercepts that are visible. So I probably did something like, let's see, I probably did something like this. Too much. There you go, maybe something like that. Yeah. So notice I still have 5 directions, up, down, up. But now, since I shifted it so far down, there's only 1 x-intercept now. So again, it doesn't have to have 5 x-intercepts. I can shift it and make it not the case anymore. But nonetheless, it has 5 directions, 4 concavities, and definitely arms in opposite directions. Okay, so now what I want you guys to do is go look through that document really carefully and go look at the vocabulary. I've been using some of the vocab in this video, but go check out the vocabulary, read it very carefully, try to make sense of it. And then after you've done that, go watch the next video, which goes over how to apply that vocabulary to a given polynomial graph. All right, thanks for watching, guys.